All right, hello Calc 3 and welcome back to another video. Today we're going to be covering section 11.4, or maybe it's better for me to say in this video, we're going to be covering section 11.4, which is on graphing polar coordinate equations. I wasn't really happy with the pace of the last video. I just thought that it was kind of slow for the material that's being covered. So I think it might be helpful to not write, at least for now. Maybe when we get to some later chapters, maybe chapter 12 or 13, then I'll start writing again to actually slow down the pace of the videos that I'm creating. But for now, I really think that it does suffice to just take notes that I've written and talk over them, explain some things, maybe add some comments. So hopefully that's all right. So let's start off by just saying that graphing polar equations in the Cartesian plane can be difficult. This isn't really a surprise. I mean, even graphing Cartesian equations in the Cartesian plane can be difficult sometimes. That's why in Calc 1, you went through all of that trouble to figure out how to find local extrema, absolute extrema, and start graphing curves. We have the similar kind of problems when we're graphing polar curves in the plane as well. So the goal of this lecture is just to present some simple methods that can help when you have to graph polar equations without computer software. Ultimately, computer software is kind of going to be the savior when it comes to figuring out what a curve looks like. But there are times where you're not going to have software available, maybe not in the real world, but at least in this class, maybe you won't have software available. And these are just kind of nice tips and tricks to figure out what a curve looks like without going to a bunch of trouble to go open some software and graph stuff. So let's start off with some symmetry. There are three different types of symmetry that the book has listed to identify when you're trying to graph a polar curve. I'm not really sure whether there are other types of symmetry that you could also consider, but at least these are the ones that we're going to cover, and it should be sufficient. So you have symmetry about the x-axis, and I have an example here. As opposed to just reading the definition, it's probably better to actually start by just looking down at this example and asking yourself, what does this mean? What does it look like? I mean, symmetry about the x-axis just means that if my function looks a certain way above the x-axis, then it's going to have a mirror image below the x-axis. But if we have to rigorously define what that means, it means that if you have a point, call it r theta, as I have listed here, and that point lies on the graph, then it would imply that the point r minus theta also lies on the graph. So what does it look like to try and prove that a polar curve has symmetry about the x-axis? Well, you would have your polar curve, it's going to be represented as some function where r is equal to f of theta. So r is given as a function of theta. And to prove that you have symmetry about the x-axis, you're going to assume that some point, you can call it r naught, theta naught, that'll work, that's fine. Assume r naught, theta naught is on the curve. And the goal is to prove that r naught minus theta naught is on the curve. There will be an example of this at the bottom, so you can just wait for that. But this is the kind of proof technique that you'd be expecting to show that a graph has symmetry about the x-axis. And the proof technique is really the same for symmetry about the y-axis and about the origin as well. You're just changing what you're trying to prove. So symmetry about the y-axis, again, I would look at the example first. You can get a pictorial demonstration of what this means. It just means that there's going to be a mirror image of your function on the other side of the y-axis. And to define this rigorously, it means that if you have a point, r theta, that lies on your graph, then necessarily the point negative r negative theta also lies on the graph. So similar to symmetry about the x-axis. And finally, we have symmetry about the origin. So a circle seems like it's a pretty archetypal example of what symmetry about the origin would look like. It just means that if you take some point, so you can look at this point that I have here, or maybe start with this point here. So you have some point that's on your curve, you're going to call it r theta, and if you reflect directly across the origin to the other side, specifically in this case to negative r theta, then negative r theta has to be on the curve as well. And you can check just kind of going around the circle every time you have an r theta. If you reflect across the origin, say I go here and now I reflect across the origin to the other side, that point is also going to be on the curve. So the circle has symmetry about the origin. And again, symmetry is important for graphing, mostly just because it makes your life easier. It just doesn't require you to work as hard to figure out what a graph looks like, because you only really need to figure out information about one region of a graph and then use data that you already have to extend it to the rest of the graph, to finish the graph, to draw the rest of the graph on the other regions of the plane. Okay, so let's move down to calculating slopes of tangent lines for polar curves. I'm assuming that this is inside of section 11.4 because you could theoretically figure out an expression for dy dx and then use the expression for dy dx to get an idea of what tangent lines look like as you plot different points on your curve. It might make curve sketching a little bit easier, but apart from that application, it's really important to be able to figure out equations for tangent lines to polar curves as well as curves in Cartesian coordinates. So regardless of whether this has an application to sketching directly, it's important regardless. So again, we're going to be talking about curves that look like r equals f of theta, and we're graphing them in the xy plane. So the slope at different points is given by the change in y over the change in x, which is what we're used to. But remember, you should remember from Calc 2 that when you talked about parametric equations, dy dx, sometimes it's going to take a little bit of extra work to calculate what that is. Dy dx is not the same as dr d theta. So if you took your curve r and you calculated r prime with respect to theta and submitted that and said that that was dy dx, you should not expect too much credit. They're just very different things. So I'm going to prove that to you here, that they're different things. So let's assume that we have a curve r equals f theta right here. Then from the equations that we discussed in the lecture previous to this, those 4 equations that allow us to go back and forth between polar coordinates and Cartesian coordinates, we can actually express this curve as a couple of parametric equations in theta. So x is going to equal r cosine theta, which also happens to equal f of theta cosine theta. So this is just a substitution using the fact that r is equal to f of theta. And likewise, we can write y as f of theta sine theta. And so once we get to this point, once we represent the curve as parametric equations, then we can use things we already know about parametric equations to calculate dy dx. So dy dx is going to equal dy d theta over dx d theta. And now to calculate dy d theta, we're going to take the derivative of f theta times sine theta with respect to theta. So we'll use the product rule. I'll draw a little arrow there. So dy d theta ends up becoming this when we take the derivative of f of theta sine theta, and dx d theta ends up becoming this when we take the derivative of f of theta times cosine theta. And here we are using the product rule. And this leads to an important theorem that you should know. So if you're given a polar curve, r equals f of theta, in the xy plane, then the equation for dy dx in terms of r theta is given by this here, which we just derived. And this holds as long as dx d theta is not equal to 0, because if dx d theta was equal to 0, this equation would require us to divide by 0 here. We'd have a 0 in our denominator. So this is probably the most important theorem to take from this section. And here's a little bit of an interesting corollary to the theorem. So let's assume again that we have this curve r equals f of theta, and let's assume that the curve goes through the origin at some theta. So I'm going to call that theta theta naught. Then 0 is equal to f at theta naught, which implies if we use this equation up here that we just derived, that's going to imply that f prime of theta naught times sine of theta naught divided by f prime of theta naught times cosine of theta naught is equal to dy dx at that theta naught. And the f prime of theta naught will cancel with the f prime of theta naught on the bottom there. And we're just left with this sine of theta naught over cosine theta naught, which is equal to the tangent of theta naught. So if you have some theta such that when you plug it in to f of theta, you get that r is equal to 0, it means that the slope of the tangent line at that theta value, so at the point 0 theta naught, is going to equal tangent of theta naught. And this again can be helpful when you're sketching. We're actually going to use it in the example that's right down here. I'm also realizing that I said I wasn't going to write on the screen, and now I'm finding out that I'm writing all over the screen. But that's okay. So, okay, let's move on to the example. So we want to graph the curve r equals 1 minus cosine theta in the xy plane. So this is a polar curve. We're given a function in terms of theta that outputs a radius r. So in the solution, it's probably best to look for symmetries first. Make sure that we can cut down on work as much as possible. So first, let's look for symmetry about the x-axis. And here's where you can start getting the idea of how the proofs might work for these symmetries. So we're going to assume that some point, call it r theta, is on our graph. Then this implies that r is equal to 1 minus cosine theta. And over here, this note is super important in this case. For all theta, cosine theta is equal to cosine of minus theta. This is a trig identity that you should know. And so we can go from this equation, r equals 1 minus cosine theta, and it implies that r is equal to 1 minus cosine of minus theta, because cosine theta is equal to cosine of minus theta. And therefore, r minus theta is also on the graph. And because our point r theta was arbitrary and r minus theta is on the graph, it means that for all points r theta, r minus theta is also going to be on the graph. Therefore, the curve does have symmetry about the x-axis. So now let's look at the y-axis and the origin. Do we have symmetry about these things? In both cases, the answer ends up being no, and to prove it, you can just pick a point such that the condition for symmetry is not met. So for the y-axis, we can pick the point 1 pi over 2, and that point is on the graph. You can verify that it's on the graph. But minus 1 minus pi over 2 is not on the graph. And this implies that we do not have symmetry about the y-axis. So if you need to check the calculations there, I encourage you to just pause the video and make sure that that's actually correct. And now we can move on to the origin. So 1 pi over 2 is also on the graph, as we already said for the y-axis here. But in this case, we want to show that negative 1 pi over 2 is not on the graph. And it is true that negative 1 pi over 2 is not on the graph. Again, if you need to, pause the video and just make sure that that calculation makes sense to you. So we only have symmetry about the x-axis, not about the y-axis or the origin. So after that, it's beneficial to notice that the curve starts to repeat when theta is equal to 2 pi. And the reason the curve starts to repeat is that cosine of theta has a period of 2 pi. So let's assume that we start sketching the curve at theta is equal to 0. And then we keep increasing theta until we get to 2 pi. Once we get to 2 pi, we're going to be right back where we started and the cycle will start again. So we're only going to worry about graphing the curve from theta is equal to 0 to theta is equal to 2 pi. And more than just this, because of the symmetry that we just established, let me highlight this. Oh goodness. Because of the symmetry that we just established about the x-axis, because we're only graphing from theta is equal to 0 to 2 pi, we actually only need to figure out what the graph looks like when theta is between 0 and pi. Because once we do that, we can reflect our graph about the x-axis and get what the graph looks like for theta between pi and 2 pi. We also want to note that the graph passes through the origin at theta is equal to 0. And as we established right below the theorem above, when the graph passes through the origin, the slope of the tangent line at that point is going to be equal to the tangent of that theta value. So in this case, theta is equal to 0, meaning that the slope of the tangent line at 0, 0 has to be equal to the tangent of 0, which is equal to 0. So the slope of the tangent line at the origin when we start sketching our curve is going to be 0. And now we can just about finish off our sketch of the curve here. So this table on the left is just a few theta values and the corresponding values of r that we can plot directly into the plane here. Those are represented by the dots in red. So here I just picked some convenient theta values that made r easy to calculate, and the book did the same thing, just picked convenient theta values that made r equals easy to calculate, and we plotted them. And then you can draw a smooth curve. If you look at this curve here, this smooth curve that's going through the red points above the x-axis, and once we draw that curve, because we have symmetry about the x-axis, we can just finish off the graph here and draw what the graph looks like on the side of the plane that's lower than the x-axis. Okay, and that's the only example I'm going to give for sketching a curve. There might be a little bit of homework from this section, maybe a couple of problems. You really should just be kind of familiar with how you can get an idea of what a curve looks like, a polar curve. It doesn't need to be perfect, but it is going to be helpful when we get to chapter 15, and polar coordinates are going to be used heavily, as well as a different kind of coordinates called spherical coordinates that we'll get into later. So just make sure that you start to get comfortable with polar coordinates and sketching some things. I'll give you some homework to assist with that. And then lastly, to be honest, most of the time, it's going to be most beneficial for you to just take a polar curve or a Cartesian curve and plot it using some kind of software that you find online. I said in the video for the syllabus that this class is very graph heavy, especially when we get into multivariable functions with 3 or more variables. The course becomes very graph heavy, and software is going to be super, super helpful. So keep that in mind as well. Most of the curves that you could come up with would be curves for which you would kind of need to use software to graph it. These should just be some tips and tricks to make it helpful when you don't have software available or if you don't want to get software out. Okay, so that's the end of this video. I should be uploading the video for section 11.5 pretty shortly, so look out for that.